In this video, we're going to look at trig ratios. Our objectives are to find the sine, cosine, and tangent of the acute angles and use the trig ratios to solve real life problems. In history, it was found that the same two sides of any similar right triangle always held the exact same ratio. Um, they named these the six trig ratios. Now, we got three of them that we're going to focus on here in our geometry class: the sine, cosine, and the tangent. They are abbreviated with the SIN, COS, and TAN. So, along with understanding those different trig ratios and what they represent, the sine, cosine, and tangent, first we have to name our different sides of our triangle. So we know every right triangle has two legs. So being that we are working from uh, one of the acute angles, we're going to call one leg the opposite leg. That's a leg that's across from the given angle. We're going to call one of the legs the adjacent leg. That's the leg that's next to the given angle. And then you have your hypotenuse. The hypotenuse doesn't change no matter which of the acute angles you're working from, because it is always the side that's directly across from the right angle. These names are dictated by which acute angle that you are working from. Different angles will give you a different perspective on the side names. This slide shows a great representation of how the perspective of the acute angle affects the side names. We have here marked on this right triangle angle C, which is the right angle. We know that no matter what angle we're working from, which of the two acute angles, that the side across from angle C is going to be the hypotenuse here. Now, if we start looking here at angle A is one of our acute angles. The side that's directly across from angle A is what we will call our opposite leg, and the side that is next to angle A, or the leg next to angle A, is what we would call our adjacent leg. Now, if we switch perspectives to angle B, what that does is it kind of flip-flops things around. So now if we're up here at angle B in red, we go across to the opposite leg, that is now going to be over here. That's the leg that's directly across from angle B. This is now the side that is next to angle B, so this side would be called the adjacent leg. We've color-coded this to help try to keep it straight of where the opposite leg and the adjacent leg lie according to which angle or which acute angle you're looking at, angle A or angle B. We would never call a leg opposite or adjacent from angle C. We will not be working from the right angle with trig. Trig is designed to only work from the two acute angles of a right triangle. The sine ratio has been assigned the opposite side over the hypotenuse to create its ratio. So if we're looking at the sine of A, that gives us our perspective angle down here in the bottom right. The sine of A, the opposite side would be x. So we would put the x on the top of our fraction. The hypotenuse in this triangle is represented by z. So our ratio for the sine of A would be x over z. We could change perspectives here and look at the sine of B. The sine of B, if we look at the opposite side from angle B, that opposite side would be y. So the y goes on top. The hypotenuse doesn't change. It never changes within a right triangle. So the hypotenuse is going to be z. So we have the sine of A, which is at x over z, and the sine of B, which is y over z. The cosine of an angle has been assigned the adjacent leg over the hypotenuse. So if we look down here at angle A, if we want the cosine of angle A, we're going to want the adjacent side, which is the y, and then we're going to put that over the hypotenuse, which is z. So our cosine of A is y over z. Now we can switch our perspectives around here and look at the cosine of B. Looking at the adjacent side, that to B would be x. X goes on the top of our ratio. And then on the bottom of our ratio is going to be the hypotenuse, which is z. So the cosine of A would be y over z. The cosine of B would be x over z. Our tangent ratio has been assigned the opposite side over the adjacent side. So if we look at the tangent of A, our opposite side from A would be x. That goes on the top of our ratio. The adjacent side from A is the y, so that would be the bottom part of our ratio. To change our perspective to angle B, the tangent of B, opposite side would be now y. Y goes on the top for tangent B. And the adjacent side from angle B would be the x, which puts it on the bottom. So the tangent of A is x over y. And the tangent of B would be y over x. You can see here that the tangents of the different acute angles are reciprocals of each other. That will always hold true. A nice little memorization tool that we picked up quite a few years ago was the little made-up word of SOHCAHTOA. Each letter of the word SOHCAHTOA stands for a part of the trig ratios. So you can see here that I have SOHCAHTOA broken up into the three colors or the three portions. The black one represents the sine function. You can see here the S stands for the sine, the O stands for the opposite, and the H stands for the hypotenuse. So you can look at the word SOHCAHTOA and know that we're looking at sine equals opposite leg over hypotenuse. The cosine here in blue is a similar setup. We're looking at the cosine of the angle is equal to the adjacent leg over the hypotenuse. Cosine of the angle equals adjacent over hypotenuse. And then the red part, the tangent, also follows the exact same setup. The tangent, the t, is equal, the tangent of the angle is equal to the opposite leg over the adjacent leg. So just by knowing that word SOHCAHTOA and being able to spell it, you can pretty much pull out your trig functions right out of that word. Sine of the angle is equal to the opposite leg over the hypotenuse. Cosine of the angle is equal to the adjacent leg over the hypotenuse. And the tangent of an angle is equal to the opposite leg over the adjacent leg. In our previous video, we showed you finding the different trig ratios using different variables. In this one, what we're going to do is we're going to actually use some numbers in here and show you that both the fractional form and the decimal form of each of these. So looking at the sine of S, we know that we're looking for the opposite over the hypotenuse. So if we take sine of S, we're down here in the bottom right corner. The opposite leg is 5. The hypotenuse is 13, so we would go 5 over 13. Now, if this fraction is something that you can reduce, you want to reduce it. If they're asking for the fractional form of the ratio. If they're asking for the decimal form for this ratio, you would go ahead and just simply divide this out, 5 divided by 13, to get your decimal form. It is pretty much a standard rule that when you're looking at these sine, cosine, tangents, that a lot of times you go maybe 3 to 4 decimal places on these. So don't be surprised if you see larger decimals than you're used to. So moving on to the cosine of S, we're looking for cosine to be adjacent over hypotenuse. So we're down here on the S angle again. The adjacent leg would be our 12. The hypotenuse is 13. So our fraction would be 12 over 13. It does not reduce, so that's our fraction we would go with. And then we would divide that out to get the decimal for that ratio, which is a 0.9231. And then finally for angle S, we could find the tangent. Tangent is opposite side or opposite leg over adjacent leg. So our opposite leg here is 5. Our adjacent leg is 12 from angle S, which would give us a 5 over 12, which simplifies down to of 0.4167. Before we go much further, you want to make sure your calculator is in the correct mode. If your calculator is not in the correct mode, you could go through all of these trig problems and do everything 100% correctly and have every answer be wrong, and that would be a terrible thing. So what I ask is that you memorize one of your trig functions, and that trig function I ask you to memorize is the tangent of 45. The tangent of 45 is always going to be equal to 1 with no decimal afterwards. It's a nice, perfect, easy one to remember. A lot of the rest of them are irrational numbers. There's a couple that are not, but most of them are irrational. Tangent 45 is probably the cleanest one you could come up with. So angles can be measured in two ways. That's one thing to keep in mind here. And that's where the discrepancy comes in your calculators. Most of the time, all the way up through about geometry and past geometry a bit, we measure angle in degrees. That's the most common way that angles are measured. And that's what we'll use throughout the rest of this course in geometry. But once you get up into pre-calc and above pre-calc, there will be times where you're going to measure angles in what are called radians. At this point, don't worry about what a radian is, but know that it's another measurement of angle, and that's not the mode we want our calculator in. So if we type in tangent of 45 and you get an answer like this, you get a 1.6197. That means it is not a perfect one and it's not in the correct mode. So what you have to do is you got to go into your calculator. We'll pull a calculator up here so you can take a look. Here's a calculator. You want to go into your mode, and you want to go down right about here where you can see radians and degrees. I'm going to try to detach the LCD here so you can see it a little bit little larger. And you would go down to radians, go over to degrees. You would select enter so that your degree is highlighted, and then you would go ahead and exit out of that, and now you're ready to go. Once you exit out of that, if you type in tangent 45 again, you see a 1. If you have one of the newer TI 84s, you'll see the degree word right up on the top here. You might see radian and you might see degree, and that's a nice little feature of those calculators. When we start digging into the different equations that are created by our trig ratios, there are three different positions in which you will find your variable. You'll find some equations end up with the variable in the numerator position of the ratio. You'll find some equations will have the variable in the denominator portion of the ratio. And then you're going to find some equations that have the variable inside the trig function itself. So let's take a look at those different equations, and I'll give you a little examples of how I would go about solving those equations. Here's a sample of an equation you might come across where you've set it up, you got the cosine of an angle equals the adjacent leg over the hypotenuse. You plug in your values. It looks like here you got a 15-degree angle. You have a hypotenuse that has a length of 50, and your adjacent leg is what you're trying to find, represented by the variable s. Now these are probably the cleanest setups that you're going to run across on these with a variable in the numerator. Since it's division and you're dividing the variable by a number, you would simply multiply both sides by 50, getting these 50s over here to cancel each other out, leaving you with the equation s equals 50 times the cosine of 15. Now, of course, you're making sure that your calculator is set in the correct mode, and you would type in 50 times the cosine of 15. As a rule, I usually tell my students, make sure if the calculator opens parentheses, make sure you close them just out of habit so that you don't run across any simple mistakes on how you entered it into the calculator. We get an answer here of 48.29, and that's what we're looking at for our final answer for this question. in this sample equation, what I have set up here, we have a sine equation. You got the sine of the angle equals the opposite leg over the hypotenuse. So in this problem, I put in an angle measure of 42 degrees. We have an opposite leg that's 33, and a hypotenuse, which is represented by the variable v. Now, what I've chosen to do here is I look at this as a ratio. Every single number, and this is a number, this is a decimal. Remember when we had the sine, cosine, and tangent written as a fraction and as a decimal. This whole unit right here is a number, and we can put any number we want over 1. So the way I choose to look at this is as a proportion, where you got two fractions that are set equal to each other. One of the rules that we cover when we look at proportions is um, based on the idea that when we cross multiply, we are going to have this sine of 42 times v, and we're going to have a 1 times 33. Well, if I were to take the sine of 42 and the v and flip positions around, kind of do what I call a diagonal exchange between those two positions, and we go to do our cross multiplication again, we will still have 33 times 1, and we will still have, up here would be the v, and down here would be the sine of 42. Everything is still lined up perfectly if we exchange things diagonally. So that's how we end up with this result down here. So you'll hear me talk about doing a diagonal exchange, and that's exactly what we're talking about. Now what that also does for us is it gets the v by itself. So now we can just take our calculators and type in 33 divided by the sine of 42, giving us 49.3 for our answer. Here's our last equation type that you'll run across. This one right here, you can see that we have a missing angle measure. So we got a sine of an angle equals opposite over hypotenuse. And the angle measure that we're looking at here is our variable. That's what we're trying to find. Our opposite leg is at 33. Our hypotenuse has a measure of 61. So now to make this work, we have to break the function of sine, or that label of a sine, off of the x. We got to get rid of that. So what I like to talk about on this is how do you get rid of a square root? Well, to get rid of a square root, you got to square both sides. You have to use the inverse operation to break that square root away from a variable like an x. So it's the same idea with sine, cosine, and tangent. But when you're dealing with sine, cosine, and tangent, they do have an inverse operation. They are simply called the inverse sine, inverse cosine, and inverse tangent. So right here I have the inverse sine of the sine of x. Well, the inverse sine and sine are going to counteract each other, leaving you with just an x value on the left side of this equation. And if we do the inverse sine of the left side, that means we have to do the inverse sine on the right side. So what that's going to do, like I said, the inverse sine and sine counteract each other, leaving you with just an x. Over here on the right hand side, you have the inverse sine of this entire side, which is 33 over 61. And this is where the parentheses are important when you type that into your calculator. So we're going to go inverse sine of 33 over 61. The inverse sine is located on the calculator directly above the sine key. So here's my sine key on my calculator. Directly above it in light blue is the inverse sine. If you have any TI-84, you'll see it in that position. To get that function, you would have to use the second key and then the sine, and they'll type in the inverse sine for you. So our answer to this question is we have a 32.7 degree angle. Let's look at a full question here. So you're looking here at a triangle that's given to you, kind of a standard looking question for a trig question. They give you an angle measure. You have an acute angle down here in the bottom right that is 23 degrees. You have a length here that's 34 and a length here that is s, and we're trying to find s. So the first thing you want to do is identify where your angle of perspective is. So we're down in the bottom right corner here. And then based on that angle of perspective, we want to know what two sides we're working with. So the 34 is our hypotenuse because that's the side that is directly across from our right angle. The S is the leg that is right next to the 23, so that's our adjacent leg. So we're looking for a trig function for this angle, 23, that deals with hypotenuse and leg. So we pull up SOHCAHTOA. We can see here that the sine is the opposite in hypotenuse, the cosine is the adjacent in hypotenuse, and the tangent is the opposite in adjacent. So we want to use the cosine since that relates to the two pieces of information that we are currently using. We will ignore the other two parts of the SOHCAHTOA. We'll write out our equation. The cosine of the angle equals adjacent over hypotenuse. We'll plug in our values. Our angle measure was 23. Our adjacent side was S. Our hypotenuse had a length of 34. The variable is in the numerator of our ratio, so we're going to multiply both sides by 34 to get our 34s to cancel out on the right-hand side, leaving us with the S. We would type in 34 times the cosine of 23 to get a value of 31.297. Here's another standard example of a right triangle trig. Very similar to the last one, but instead of having that adjacent side over here, we have that opposite side here of the T. So again, if I were to approach this problem from scratch, I would look at my angle of perspective. I would identify what other two sides I'm looking at using. I'm going to use my hypotenuse, which is 34, and my opposite leg, which is T. This is the opposite leg because it's the leg that is directly across from the 23. Now I'm going to look at SOHCAHTOA and figure out what I want to use. I need something that uses opposite and hypotenuse, which is the sine. So we're going to use that sine function. We're going to ignore the other two. We're going to write our equation. The sine of the angle equals the opposite leg over the hypotenuse. Then we are going to plug in our values. So my angle value here is 23. My opposite side is T, represented by T. My hypotenuse is 34. I have the variable in the numerator, so I'm going to multiply both sides by 34 to get the 34s on the right side to cancel out. I have T equal to 34 times the sine of 23. I'm going to grab my calculator, calculate 34 times the sine of 23. We get an answer of 13.285. In this example, we're going to find our missing value of V. It's another right triangle trig problem. We're going to first start off by identifying where our angle of perspective is. Our angle of perspective is down here in the bottom left. It's 70 degrees. We have this side up here, which is 9, and this side here, which is V. Once we establish that angle of perspective, we're going to identify what sides we're working with. So this side down here would be our hypotenuse. That's the side that's directly across from our right angle. This side up here is our opposite leg, the side that's directly across from our angle of perspective. Now we're going to figure out which of the trig functions it is that we would use for this problem. We need the one that is going to work with the opposite leg and the hypotenuse. So that looks like it would be the sine function right here. Sine is opposite in hypotenuse. We're going to ignore the other two and we're going to set up our equation. The sine of the angle is equal to the opposite leg over the hypotenuse. Plug in our values. Our angle is 70 degrees. Our opposite leg has a length of 9. Our hypotenuse has a length of V, or represented by V. Now because the V is in the denominator of our ratio, we're going to diagonal exchange that with the sine of 70. Remember, the sine of 70 travels as a full unit. You cannot break it up as we do this, as we do our algebra here. So we're going to exchange those two pieces. What that does is it puts the V up here on the left-hand side by itself. It moves the sine of 70 down into the denominator of the ratio as a full unit. Now at this point, you're able to calculate 9 divided by the sine of 70, which gives you a value of 9.578, which is our solution to our problem. So this side length here, the hypotenuse, would be 9.578. In this problem, we're going to find W. We have a right triangle problem with an angle of 70 degrees. We have a side up here at 9 and a side here that is what we're trying to find. So this is set up as a trig problem. So we're going to start off by looking at our angle of perspective, which is down here in the bottom left corner. We're going to identify what sides we're working with. The side up here would be our opposite leg, because that's the leg that is directly across from the 70 degrees. And then we're got to look at this leg, which is W, which is the leg right next to that angle. So we call that our adjacent leg. We need to identify which of the trig functions it is that we're going to use. Looking here, it looks like the sine works with opposite and hypotenuse. The cosine works with adjacent and hypotenuse. The tangent works with opposite and adjacent. That's what we have, so this is what we want to use, the tangent function. We're going to ignore the sine and cosine functions for now. We're going to set up our equation. Tangent of the angle is equal to the opposite leg over adjacent leg. We're going to plug in our values. Our angle measure is 70 degrees. Our opposite leg has a length of 9. Our adjacent leg is represented with a length of W. So because our W is in the denominator of the ratio, we're going to diagonal exchange this. The diagonal exchange puts the W up here on the left, moves the tangent 70 down to the denominator on the right, putting the W by itself, which is what our end result wants to be, or where we want it. So now this is something we can calculate. Type in 9 divided by the tangent to 70. We get a value of 3.276, which is our answer for W. In this problem, we want to find our missing angle measure of x, and we're given two sides on our right triangle. So to be able to find our angle measure of x, what we need to do is we need to set up a trig problem. Our angle of perspective is down here in the bottom left corner, which is the x. We need to identify our sides. So we have an opposite leg. The 12 is directly across from the x. And then we have a hypotenuse, which is the side that's directly across from our right angle. So we're looking for a trig function that uses opposite and a hypotenuse. So looking through here, we got opposite and hypotenuse right here with our sine. So we're going to go ahead and use sine, ignore cosine and tangent. We're going to set up our equation, plug in our values. Our angle measure is x. Our opposite leg length is 12. Our hypotenuse has a length of 13. Now this sets up a new perspective for us. We need to get the x out of the sine function. Now the sine is a function, so what we have to do to get rid of that sine function is use the inverse of the sine function. So we're going to give ourselves a little bit of room on either side of the equation, and we're going to start off by taking the inverse sine of that left side, and then what we do to the left side, we have to do to the right side, so we're going to inverse sine the right side also. Now, inverse sine and sine, they cancel each other out, leaving you with the value of x. And then on the right side, what we have is the inverse sine of 12 over 13, which is perfect for us to calculate. We can go ahead and use the inverse sine function on our calculator of 12 over 13. Make sure you lock that whole fraction in the parentheses, and then that gives us a value of 67.38, which is the angle measure of our triangle. In this example, what we're going to do is we're going to find our new angle x. Angle x is up here in the upper right corner. We're given two side lengths, so this is set up as a trig problem. Anytime you got the one angle and two sides, chances are you're looking at probably some kind of trig. So we're going to locate this as our angle of perspective. We're going to look and name our two sides that are in relationship to that angle of perspective. We have a hypotenuse because the 13 is directly across from our right angle. And we have the 12 up here, which is the leg that is right next door to our angle. So that's going to be our adjacent leg. So we need something that trig function that works with the adjacent and the hypotenuse. So looking at SOHCAHTOA, we got our opposite hypotenuse here. Don't need that. We have adjacent and hypotenuse here. That's exactly what we have. So we're going to use the cosine function. We're going to get rid of sine and tangent. We're going to write our cosine equation. We're going to plug in our values. Our angle measure is x. Our adjacent leg has a length of 12. Our hypotenuse has a length of 13. To get the x out of the cosine function, we have to use our inverse function of cosine, which is the inverse cosine. So we're going to do the inverse cosine of both sides. Inverse cosine and cosine cancel each other out, giving you just the x. And now we're left to calculate what the inverse cosine of 12 over 13 is. We go ahead and type that into our calculator, and we get an answer of 22.619 and so on. So it's probably going to be a 22.62 degree angle. Here's one of our real life examples where we're trying to find the height of a tree. What we're given here is that you calculate your angle of elevation. That's the angle from our lowest point right here up to the top of the tree to be a 59-degree angle. And we did that from a point that is 45 feet away from the base of this tree. And we want to calculate the height. So this is a trig function that we're looking at. So what we have and what we're given in our right triangle here is that we have an angle of 59 degrees. That's from our angle of perspective down here. We have an adjacent side, which is 45 feet, and we have a height over here on the opposite side. So that's the opposite side of our right triangle. So using that we have the adjacent and opposite, we want to use our tangent function. So we're going to go ahead and plug in our values here. Our angle measure is 59. Our opposite side has a length that's represented by h, and our adjacent leg has a length of 45. Our height is, or our h is in the numerator of our problem, so we're going to simply multiply both sides by 45 to get our 45s here to cancel out. So now we just got a little calculating to do. We have 45 times the tangent of 59. We go ahead and calculate that out. We get 74.89. So 74.9 is our answer. So the tree is approximately 75 feet tall. Trig, when we use this in the real world, is an approximate answer, but it's pretty darn close to accurate when it's done properly. So we got a 75-foot tree that we're looking at. In this real life example, what we're doing is we're trying to find the distance of a ski run at a ski resort. So taking a look at this, they give you an angle of depression. That would be an example of that would be if you're standing at the top of the ski slope looking down the ski slope. If you go from an angle of level and follow and create an angle looking directly down the ski slope, you would see that it's a 20-degree, and that's what we call an angle of depression because it's looking downwards. So if you were like in an airplane looking down at an air tower, air traffic control tower, you would be looking down at an angle of depression. Now, if you're at the bottom, say you're in a group and the rest of your group's at the bottom of the slopes and they're looking up at you, the angle from level at the bottom of the hill looking up would be what we call the angle of elevation. Now, the angle of depression and the angle of elevation are always going to be equal to each other. Here's an angle of depression. Here's an angle of elevation. The reason they're going to be equal with each other is because level at the top of the hill is going to be parallel with level at the bottom of the hill, making these two angles alternate interior angles. So the angle at the bottom of the hill looking up is also 20 degrees. We're going to focus on our angle of elevation for this problem because that moves the 20 degrees from being outside of our triangle to inside of the triangle. It's going to be more valuable to us right there. Now we have two other sides here that look like they're pretty important. The D is the distance of the run of the slope, which is what we want to find. So we're probably safe leaving that as a variable for right now. The X is the vertical drop. Now that vertical drop is probably something that we need. We don't want to have two different variables in our problem, so we need to look for some other information that might help us to find that vertical drop. We see up here that at the top of the hill, we're at an elevation of 5,500 feet. At the bottom of the hill, we're at an elevation of 5,018 feet. So we can calculate that vertical drop simply by subtracting the elevation at the top of the hill minus the elevation at the bottom of the hill. 5,500 minus 5,018 puts us at 482 feet. So we have a vertical drop of 482 feet. That gives us enough information for us to calculate the distance of our ski run. So we're going to look at a little bit of trig. We're going to keep in mind we have SOHCAHTOA, we have our angle of perspective down here, we have our opposite leg here, and our hypotenuse here. So looking for our opposite and hypotenuse tells us that we're going to be using our sine function. We're going to get rid of cosine and tangent. We're going to set up our equation. We're going to plug in our values. Our angle value is 20. Our opposite side has a length of 482. Our hypotenuse has a length that's represented by d. Because our denominator has a variable in it, we're going to diagonal exchange these two values, moving the d up here and moving our sine 20 as a full unit down to the denominator. So we end up with this result down here. This is something that we can calculate here, the 482 divided by the sine of 20, which gives us an answer of 1,409.3 feet. That is the approximate length of that ski run at this ski resort. As we leave this lesson, we want to have some goals in mind that we want to leave this lesson with. First of all, we want to be able to identify and calculate the three trig ratios we use in geometry: the sine ratio, cosine ratio, and tangent ratios. We want to be able to solve right triangle problems by using our trig ratios. If we are given any acute angle and a side length of a right triangle, we should have the ability to calculate a missing side length using trig. And if we're given two side lengths of a right triangle, we should have the ability to calculate the measure of a missing acute angle. And finally, we need to be able to apply these skills to real-world situations, being able to indirectly calculate the lengths and angle measures of real-life objects. Thank you for listening.